Okay, so that's this is again what we are talking about. So originally all our lights is on, right? All our lights is on, and now if I push a button, right, and the lights on itself will be changing status, and all of adjacent one will also change the status. If I push this button, and this will be off, 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 on, right? So if I push this button, then this becomes off, on, right? If I push this button, then this becomes on, off, on, right? If I push this button, then it becomes off, 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 off. Now the question basically is question. If all vertex lights of a connected graph G are on, is there or does there exist a collection of light patterns such that when pushed let me say which when pushed will turn off all lights. The question is given a connected graph and assume that every vertex, right, original lights are all on, right? So if you can imagine, there's a building here, and then every building, every room, every room in the building, the lights is on. And now you do have a bunch of buttons, and you want to push a button. That button will control the light in the room, and also the adjacent rooms, right? If you push that button, then what you want to do is you push a few buttons, right? And you want to turn off all of the lights in the building, right? So that there exists a collection of lights, such that light button, such that when they are pushed, then that will turn off all of the lights. So for example, as I just give that to you, if it is so my previous example, what I did is I push all of these buttons. If I push all of these buttons, then turn out to be my previous example. If you look at my previous example, that turned out to be it will turn off all of the lights in the building, right? So for example, if I have a triangle, so if I just push one button, and then it's going to change off, 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 right? So we'll turn off all of the lights. So for example, if I have, say I have a circle here, and this is everyone is going to be an on, and all I need is, say I push this button and push that button, push this button, and that's going to be off, and then I have to, that's not a good one. Let me make a little bit So 6. 1, 2, 3, 4, 5. This is not 6. Yeah. Okay, so that's my graph. And if I push this button and that button, right? So if I push this button, it will turn off all of these lights. If I push this button, it's going to turn off all of these lights. And then that's going to become all lights will turn off, right? So in our example, I give that to you. Turn out to be you will be able to find some vertex. If you push the vertex, and the lights will turn off, right? So generally given any graph, and can we find a collection of all these light buttons, which will turn off all of the lights in the building, right? So answer is yes. In the reality, you will be able to do that, right? So actually, some people have already proved this result. But the problem is how this is connected to our dominating set. So the connection to our dominating set basically lies in the following interpretation. So I can change the question in our dominating set. Basically says, is there a dominating set of G such that every vertex in G is dominated by odd number of vertices. If I say this dominating set is S, then is dominated by odd number of vertices in S. Okay, so one way to interpret this problem is we can change this into a dominating set problem. Suppose question basically asks you whether you will be able to find a dominating set of S, then every vertex in this in G is going to be dominated by odd number of the coverings, right? So of the vertex in S, right? So why we emphasize this odd number? Because if you push a button in S, then all of the vertices dominated by this vertex is going to change status, right? So everyone is going to change status. Everyone is going to change status. And now if you push this button, everyone adjacent to this vertex and itself is going to be change status. And now if you have odd number, then you can change from on go to off, and then off go to on, and then go to off. So if you change from on to off, then this is just one time. From off to on, that's one time. Even number basically go back to itself. If originally it is on, then it will stay on. But if you change status odd number, right? So it change from on, off, on, and then on, off. If you change, say in this case, is you change 3 times. 1, 2, 3. It will change from on to off. Right? So that's the reason if every vertex is covered by dominated by odd number of the vertices in S, then everyone is going to change from on to off. Right? Everyone is going to change the on to off, and therefore you do find a solution to the original problem. Okay. So the way to connect the original problem with our dominating set is now I want to find a dominating set such that every vertex is going to be dominated by odd number of vertices. Odd number of the vertices in S, right? So that's all you need to do. Because I don't want to try. It's way too complicated. So for example, if I look at right, so originally this one, right? So if I pick my S, is exactly the same one. So now you see this vertex is dominated by itself and two adjacent one, right? So therefore this is 3. And if I look at this vertex, it's dominated by itself and all of adjacent one. So I have three arrows, right? That's 3. If I look at this vertex, it's dominated by these two adjacent one and 3. And then if I look at this vertex, it's dominated by this one is 3, right? So therefore, everyone is dominated by 3 times by odd number of in this case, S is V1, V2, V3, V4. S is V1, V2, V3, V4, right? Everyone is dominated by odd number. So therefore, that's the answer to this problem. If you push all of these buttons, and finally, and the whole lights will go off, right? So that's the answer to this. So for example, let me look at give you a little bit of so if I look at this example, right? So if I just pick this point, and then this is going to be S is equal to this vertex V. So now if you count on every vertex, I count the coupling number of the couplings, right? This is 1, 1, 1, 1, 1, right? Every vertex is covered by 1. So therefore, if you push this button, all of these lights will go off, right? Change the status from on to off or from off to on, right? So therefore, that's the answer to this problem. Let me give you a little bit more complicated example. So I have here, 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 here. Okay, so now I want to find the answer, right? So lights, originally assume this is my graph of the lights, and originally I assume all of the lights is on. Now I want to push a few buttons to turn off all of the lights, right? So of course I don't want to try and then find the answer. It's way too complicated. So then what I want to do is translate that into a graph theory problem. I want to find a dominating set of G such that every vertex is dominated by odd number of the vertices, right? So let me pick a few of them. So this is 1, 2, 3, 4, 5. Okay, so let me pick my S to be a collection of all these vertices. Now I want to calculate for each vertex. I want to calculate the number of the domination, right? The number of the domination. So for this one is dominated only by this one, right? So that's 1, and this one is also dominated by this one, 1. For this one, it's dominated by itself and these two adjacent vertices, right? Vertices, because they are chosen. So that's 3, and this one again, that's 3. And for this one, is dominated by itself and two adjacent ones, this one and that one, not by this one, right? So because this one I didn't pick that one, so therefore this is also equal to 3. It's dominated by three vertices in S, 1, 2, 3, right? So this one is dominated by here, 1. This one is dominated by here, and this one is dominated by here. This one is dominated by itself. This one is dominated by itself. Okay, so now if I look at my my numbers, all of these numbers are odd numbers, right? So which means if I push all of these buttons, and the whole graph will change the status from either from on to off or from off to on, right? If originally I know all of the lights are on, then if I push all of these buttons, then it will turn off all of the lights. Right? Maybe another example. Say I have say I have this example, right? So now assume I want to find a dominating set such that every vertex is dominated by all the number of this dominated set, right? So now let's look at how we are able to find that set. Let's try. One, two, three, 4, 5. Let me pick all of these five outside ones, right? And then I find this one is dominated by itself. Don't forget itself, and 2 adjacent ones, right? So that's 3. Again, that's 3. That's 3. That's 3. That's 3. Right? And for this one, it's dominated by only 1, right? So from S, so that's 1. And not by, because these 2 are not picking, right? So not in S, so that's 1. And for this one it's 1. For this one is 1. For this one is 1. For this one is 1. Okay, so then I find for each vertex it's dominated by all the number of the vertices in S, right? So therefore, if I know originally, if I know all lights on this graph is on, if I push all of these buttons, right? If I push all of these buttons, and then I will find all lights will turn off. Right? So I don't have to go through the whole process, and I just count the numbers and notice all of them are all the numbers, and then now I know if I push all of these buttons, all of these 5 buttons, and now I know I will turn off all of the lights. Okay, so this is kind of one nice application of what we learned today for the dominating set. Okay, so basically this is what I planned for today. So we look at the dominating set. Basically is vertex to vertex, right? So that's a dominating set. Dominating set. Remember from the last time, edge to vertex, and we also have vertex to edge, right? So this is some beta G, beta prime G, or beta G. Right? So we do have quite a lot of constants introduced for different graphs, right? So this is independent. In this case, independent. This covered, right? And this is dominant. So, but the idea, philosophy are the same. Idea are the same. We follow the same idea. Okay, so that's all for today.